So thank you for attending the first round of talks. It's with great pleasure that I introduce Alan Shreve, who will be giving a talk on event sourcing systems with etcd.
Good morning, everyone. So my name is Alan. I'm at Inconceivable on the internet, and I'm the creator of NGROK.com. For background on that, because we're going to be talking a little bit about it today, it's a tunneling reverse proxy, and it's basically the best way to expose services behind a NAT or firewall to the internet for demos or webhook development or IoT connectivity. You can kind of think of it like a reverse SSH tunnel on steroids. And today, we're going to be talking about event sourcing. And like most things in computing, event sourcing is not new. Event sourcing is like cloud computing or the Internet of Things or deep learning or microservices. It's simply just the latest buzzword for something that we've been doing for a really long time, which is replicated state machines. So just a quick recap of like what that means. In an event sourcing replicated state machine architectural model, basically what you're doing is you're modeling application state as a state machine, and all of the changes to the state machine are modeled as events. And so your application is basically architected as an ordered stream of events that change the deterministic state machine. So you get all these events in, and each one of them applies a change to each state machine. And if you replicate that ordered set of events to multiple state machines, congratulations, you have like replicated state machines. This is the event sourcing model. Event sourcing, like I said, is not new. You can find it everywhere, even in things where you like outside of like the distributed systems context. Right, databases are a fantastic example where you have a master node and a slave node, and it replicates statements to a slave. Even like a log structured file system or journal file system you could think of as like a snapshot and a journal of the next set of changes that are going to be applied to it, or in like a log structured file system where all of those are essentially just a rotating log of all the changes that have been made to the file system. Even networked games basically run this same model, where in order to replicate the state of a game to everyone, whether you're playing like an RTS like StarCraft or something like that, it's often modeled as, okay, all of the players put in these commands and you replicate the commands to everyone, and everyone runs the same state machine to update their local state of what the game currently looks like. And it's a really nice model. It has really nice properties, and it's conceptually very simple, right? And so that's why it's found a lot of adoption. It's become popular because it elegantly solves a number of difficult engineering problems that are faced by modern software enterprises. Specifically, we've discovered that a system built on these principles is really the cornerstone of like a solid data pipeline, from working with your working set of data, and then basically creating this pipeline afterwards where you can do real-time stream processing on all the changes that are happening to your system. You can ship everything off to cold storage for like OLAP processing and various things like that. And basically, you're just hanging new consumers off the end of your replicated log of events, and that allows you to basically push data into all sorts of new different types of data models, which we found is helpful. There's another acronym pattern for this called CQRS, which really doesn't matter what it's called, but the idea is that you can basically, if you have an event log, you can basically store your data in any number of different ways, each tailored to the particular type of operations that you would like to do on it, right? So if you want to do like very long-term queries, then there's a good way to store data for that versus, oh, I want to do stream processing over the last 10 minutes of events to make real-time decisions. So what we're going to be talking about a little bit today is two challenges that I was facing while building NGROK, where I ended up employing an event source model to handle those, to tackle those solutions. The first problem is the propagation of tunnel state to NGROK's edge nodes, the routers or balancers. And the second one is the geo-replication of global data to all of NGROK's regions. So we'll take a quick look at what each of those problems look like, just to give you an example, just to give you an idea of where we're going. So when you connect an NGROK tunnel, basically it's a process that you run on your machine. It connects to this service and gives you a public endpoint that will route incoming connections to your local machine. And when you connect an NGROK client to the service, it basically connects to one of many tunnel servers running inside of the cluster. And so when an inbound connection arrives to NGROK's edge servers, it needs to know where to route that connection. So basically, you need to keep a map of which NGROK hostname is where the backend is for that particular connection. So basically, the idea is that when you need a map, so when an NGROK client connects, you want it to register with some sort of map and say like, okay, the foo.ngrok.io in this case, which is the name that I'm binding for, is hosted on tunnel server A. So basically, when a connection comes in, NGROK's edge nodes pull out connection information. They pull out the host header or the TLS SNI extension data. And then their question is like, how do I map that? Like which tunnel server is this located on? So they're going to look it up in the map. This data changes extraordinarily rapidly. Tunnels go up and down very frequently all of the time. So changes to the state need to be available immediately, right? As soon as someone connects a tunnel, it needs to route properly. Basically, if the internal map is slow for any reason, like a connection is going to fail when it should have succeeded. That's a very poor experience, like a very poor customer experience if it happens. It's even worse if it's like part of some sort of production use case where you started a tunnel and after that you told some other system, hey, it's online, go make a connection, and it fails. The second use case that we'll talk about a little bit later is the replication of global data. NGROK is architected similar to AWS. Basically, each region stores region local data locally. So the region data for the US region is stored in the US servers and the European data is stored in the European servers. That being said, just like in AWS, there is some data that is relevant to all regions. And it's what you would expect. It's things like credential tokens, account information, like is this account suspended or not, things like that. And that data needs to be replicated to the global regions for read-only access. Basically so that when the local regions need to perform operations and check like, should I allow this operation, that they can make a very quick decision, don't have to go to the global region to answer that question. So just as an example, like when you start an NGROK tunnel, the auth token credential that you use is checked for validity, and then it pulls out the account data, and then it checks that validity as well and permissions. And it's the same sort of thing. When this data is manipulated, it needs to be replicated to the global regions, ideally as quickly as possible. It's, again, a poor customer experience if someone like signs up and then they go to start a tunnel and it fails and tells them, no, your account doesn't exist. But even worse, there are tons of clients who basically use NGROK in an automated way where they will create a credential via an API, and then immediately after they've created that credential, will try to use it. And so that failing basically is a production failure of the service to deliver. So the question that was really the problem being solved was like, how do you effectively store this data in a way that you can replicate it to all the regions quickly and efficiently? So these two problems, like while I was working them, seem to like lend themselves to this event sourcing model. You're basically looking to push the state somewhere else, but keep replicated copies of it. So that seemed like a really good fit. And so, I spent a lot of time like reading and learning and listening to presentations about how other people have approached architecting these systems. And you notice that people who build these systems, like the modern architectures for them tend to follow a number of different like distinct design patterns. And so I wanted to kind of give you an idea of like what those look like for people who are building these systems, and kind of like how NGROK's problems like mapped into these different solutions and implementations. So this is the simplest kind. It's basically the idea is that as you have events, you write them to an event bus, and then you hang consumers off at the end. This is as dumb and possibly stupid as you can get of an implementation, but it's very simple and it works. The problem with it is that you can't, basically when you write to the event bus, you're basically saying this event happened, and so it only really works for situations where events are facts, like they're guaranteed to have happened. There's no question about like, is this operation allowed to happen? So this is really good for systems where you're like keeping track of logs, like, oh, I want to create an event for every time someone made an API request into our system, right? Where it's like, obviously it happened, we can record it, and we can hang consumers off at the end to do interesting things and keep the state of what has happened. But then you always end up in a situation where you're like, you might end up in a situation where you're architecting a system and someone says, I want to make this change, I want to manipulate the system in this way, and now you have to say something like, is it allowed to happen? Is this a valid change, right? And so in this type of system, you actually need to basically keep some state that you're going to use before you put the event onto the event bus. And so this is kind of like what I call a forked write design, where basically what you do is you keep your state in a traditional database and you execute a transaction, and when it succeeds, if it succeeds, you've agreed that it is a valid operation, then you write it to the event bus. The trouble with this is the typical like, well, what happens if writing to the event bus fails? Then all of your consumers are going to be out of sync. So this kind of system is only acceptable for systems where message loss and ordering guarantees are not priorities. And there are some systems like that where this is a simple model and that will work, where you don't care too much about that. Ordering is the other problem, right, where you have two consumers writing to the database and they both create transactions, and one succeeds before the other, but when they write to the event bus, it happens in the opposite order. So that's also tricky with this sort of system as well. So the next one is what I call like the database OPLOG pattern. And this one has been gaining a lot of traction recently, and I find it a really attractive pattern, but it does have its problems. In this type of system, basically, all of the writes for your system are validated and executed against like a typical CP database system. And what you do is you run a separate process pointed at that database system that basically watches the oplogs or the replication log of that particular database, and then it pushes each change onto an event bus. These systems basically, they have a couple nice properties. One is they get a really nice total ordering because the database decided on an ordering for those transactions. So that's great. You don't have to worry about that. And it avoids data loss, right? Because it's basically reading off of this replication log and leveraging any sort of failover system that you already have for your database system. That being said, I mean, like, who knows a database system that just like does this out of the box? Like MySQL doesn't do this, or Postgres, or Oracle, or any of the ones that you're, used to using. So there are a number of third-party tools that have been built to kind of fill this niche, and they're mostly like open source projects from companies who had this particular problem for the technology that they use. So, like, for example, like Stripe has one called Mongo River, and Zendesk has one called Maxwell, which works with MySQL, and I forget, someone built one for Postgres called Bottled Water and things like that. There's actually an open source project that is working to kind of standardize an interface to a standard tool that you can point at any of these databases that will do that. The project is called Debezium. And they're basically trying to build this out for MySQL, MongoDB, Postgres, and Oracle. But like I said, it's all like still pretty new, and so the tools are getting better and starting to get more trustworthy, but they are still new tools, and it's important to keep that in mind because you're basically working with an interface that the designers of the database did not intend to be an interface. Like, no one was sitting there like, let's design the OPLOG so that other people can read it. That was not like an intention in designing that. And the final pattern is the one that's kind of the most flexible and most powerful. This is the LMAX architecture. It was popularized by a financial firm called LMAX. And they gave a talk about this a few years ago, and it got picked up, and a lot of people have found this to be a helpful model. So basically, it was architected around the idea of extremely high performance and very low latency, basically for doing financial transactions. And it's where, if you've heard of the LMAX disruptor, which is a very high performance lockless queue implementation, ring buffer queue in Java, that's where this came out of. So the basic idea is kind of like the first pattern that I showed you. Write all of your events directly to an event bus, but you don't just assume that they succeeded. Instead, basically, you're waiting for one consumer, that is the leader process handling application state, to basically process that event that you asked it to process and decide whether it's valid or not, and decide what the result of that operation is. And so when it decides what that is, basically, it will take that, we're not there yet. Basically, it will take that operation and then stick it back onto the event bus in a different queue. And the clients are basically listening on another queue for their results back. So this is kind of like an event bus RPC sort of pattern that you might see in like enterprise middleware patterns, things like that. The basic idea was that if you do it in this way, you can create like an extremely high performance single threaded application that basically keeps all of the application state in memory and basically farm out all of the I/O to separate threads that are basically doing the I/O, and you're interfacing via these high performance disruptor queues. This design is really the most challenging because there's so many things that you have to implement to get it right in a HA scenario. So in order to do this sort of thing, you need to have one consumer that is the leader who creates essentially the total ordering of events, the canonical ordering. And so what you're doing is you're basically building replication yourself, where the leader is responsible for creating this canonical ordering and shoving it back into the event bus on yet another topic, and you have replicas that are basically watching that stream. You have to build your own failover for when the leader fails, to pick which replica and then point everyone back at it. You also have to build your own snapshotting, right? So this is a thing that we haven't talked about yet, but basically if you have an event stream for forever for all of the changes to your application state and your process crashes and you want to load that state again, you have to start from the beginning, which could be a very long time, unless you take like a periodic snapshot where you dump the state at one point and you say all the events after this are the ones that I'll apply to get back to my current state. If you're leveraging something like a database, you already have that snapshot. It's the B tree that's on disk. Like, great, you're done. But for this kind of architecture, you have to build that snapshotting yourself. You might be saying to yourself, like, leader election, master process, canonicalized event log, snapshotting. This sounds really familiar. I've seen this before. Isn't this just etcd? And the answer is yes, this is just etcd. This is just Zookeeper. This is just your your DBMS. Like I said, this is what I was referring to at the beginning of the talk. Like, we're kind of coming full circle in that all of these are already event-sourced systems. So it's kind of weird that you might think of like building on top of them. But the reason that we tend to build event-sourced systems on top of these things is basically because they aren't programmable enough to insert our application logic into it. So we're kind of like leveraging to build interesting business logic cases on top of them, but leveraging them for different pieces of an event-sourced system. So back to like the original problems that I was talking about when building NGROK. The original design of the tunnel map actually involved the tunnel servers manipulating like a SQL database. The map was a SQL database, and each of the edge nodes, each time there was a new connection that would come in, they would basically consult the map, which was like a SQL query, and ask it like which tunnel server it was on, and then like splice the connection. As you might expect, this was extraordinarily slow. It was not a good design. And basically, I started thinking about how to re-architect this to basically support the fastest possible lookup. So the idea was that this map lookup should be in memory. So the event source system I ended up building out was built on top of Redis. And basically, it's exactly what you would expect. There's a Redis database where all of the where basically there's a map that's kept of where each tunnel is hosted, the tunnel server that a particular tunnel is hosted on. And then there's like a giant Lua script that has all of the application logic inside of it. And so I did a couple of clever things where basically I created this service where the edge nodes would basically make a call to the map service and say, hey, give me all of the state and then all of the changes, where it would basically suck down the whole state and then set up like a Redis pub sub channel to watch for events that happened afterwards. And so basically it was able to keep the entire map essentially in memory, so it's replicating all that state. So basically it is just an event source system. That being said, it has a number of drawbacks to doing this way. First, writing business logic in Lua was not great. It's just not great to like have like this one piece of your business logic in a completely different language than all the rest of your other code, if you can help it. Especially in an environment where it's not particularly testable, not easy to debug or put in tracing and stuff like that. Lots of things that you have in like whatever it is that you've written the rest of your application in, you can't like leverage all of that tooling. The other like downside is you have to maintain your own indices, right? Redis is a key value store, so if you want to support operations like I do, like get all tunnels by account, you have to build those indices yourself and maintain them, so when tunnels start and stop, you have to manipulate all of those things, essentially in atomic operations, which is why the Lua script is the key to doing that, because you basically have to manipulate a whole bunch of keys at once. And then I'm also like on the hook for doing failover, right? Redis doesn't like natively support that. There's like Sentinel, but it's not like kind of just like it happens automatically. So I basically built that first, and then I was thinking about how to do the global data replication, and thought about two things. Like one, I wanted a better system than that, and two, like it was basically like reusing Redis for this system was basically a non-starter. Basically because the limitation of first grabbing all of the state every time that there was like a connection disconnect wouldn't have worked when you're basically talking across the globe and connections fail all the time, and you can't like resend like megabytes of data and expect it to be performant or up to date in time. So yeah, I want to show you a little bit about like how that system works. So I ended up building it on top of etcd. So etcd is the store that basically powers the global data replication for NGROK's account data and NGROK's credentials data. So I'll show you a little bit of how that works. Basically, each of the regions like runs a process that's responsible for connecting to the CRED's global service that runs in the global region, which basically fronts etcd. So the actual like replications store, the actual etcd, is basically hidden behind this service that it can be swapped out later if you wanted to, and all of that is kind of abstracted away from the service regions, who basically are talking to this service and fetching the data when they need to, basically by syncing the entire state once when they come up and then streaming changes afterwards. So I'll show you some of the code. This is a gRPC interface. It's basically what all of NGROK's internal services use to talk to each other. And it's the interface for the replication of account data and creds data. And it has two operations. They are sync the base state, which is basically I came up, I don't have any state, could you please dump everything to me? And then afterwards, it is the sync updates call is I have a base state, I know the revision that it's at, please stream me all the changes from that particular revision. So you saw that the base call basically doesn't take an argument, and the updates call takes an argument, and the updates call basically takes an argument of where to start. Basically, it's just the revision number that you're really looking for. It looks more complicated in my code basically because the system was set out to not be tied to etcd, and there are a number of different event sourcing systems. If you're using something like Kafka or Kinesis for your event log, where you actually don't have a single shard that all of your events go through, you actually have multiple shards. The etcd store is actually really simple because you only think about one shard, which actually makes it really nice to work with because it's a lot simpler to reason about. And then you saw basically both of those calls return the same thing, which is a stream of items. And so I'll show you a little bit about what those stream items look like. This is not the most elegant data modeling I've ever done, but it does work. Basically, the idea is that each item that's streamed has a sequence number and then possibly an error. And if it doesn't have an error, it will have a bunch of events attached to it. And all of those events are basically a tuple of an operation and an item. And so the operation is either going to be put and then an item body, or delete and an item key. And this is what stream object looks like. So you can get a sense of like what that looks like instead of like using kind of like a polymorphic any void star sort of thing for the object. They're actually like hard coded into it, basically for type safety and ease of use. But you can see like the stream object has the things you would expect. It has a key, it has the object, and it has some metadata around like what particular version when the object was modified. These aren't actually used, but they are nice to have. So this is the actual trimmed down code of what one of the local regions will do to sync its state to the global region. And it's pretty straightforward. Basically what you're looking for is the first thing that you do is you do the sync base call to grab all the data. And then once it's synced, you'll see it says set read storage, and basically what it's doing at that point is it's saying that I have a local copy of the data, so start serving any requests out of that local data. Before it actually syncs all of that local data, it actually defers all of its calls to the global region. So that basically as soon as the process comes up, it does work, but it's slow until it actually gets a full set of state. And then basically it pulls out a stream to the global region and it runs the stream. When the stream fails, it's checking for two things that determine whether it needs to resync the entire state. So one of those conditions is like the revision is unavailable. This is the trouble that you have with event source systems is you never keep the entire event log, right? Like I was saying, you keep like a snapshot in the event since it. So it's entirely possible that you could ask the global region like, hey, can you give me events from time 0? And it will say, sorry, I don't have them. Like you're going to need to resync your state to some point where I can stream you events from. And then this is like the run call when you're actually like running a stream. So you can see like it creates like an updates request object. I don't know, can you guys actually see that? I hope so. Basically it creates like an updates request object and then calls sync updates to actually start running it. And then it's basically just iterating over the stream. So it pulls out a new object by calling the receive method, and it's looking for errors of a number of different kinds and trying to qualify which one it is, and once it decides it hasn't gotten any errors, it basically keeps a list of callbacks that it's supposed to call for each of those items. And the error logic that's, you can see like basically all of this is error handling logic, and it's basically looking for like, is this a connection disconnect, like a connection problem? Because if it's a connection problem, I can just reconnect and start streaming again. I don't really have to do anything special. It's when I start hitting like application logic errors or revision unavailable errors that I actually have to like go back and like return to the caller and let them decide what to do. There is nothing clever about this design. And that's kind of the point of it, right? Is that this should seem like a really straightforward use of etcd, where you ask etcd for a bunch of data and it hands it back to you and it says, this is the revision that I gave you all the data at, and then you create a watch on etcd and you say, stream me all these changes from this particular watch. That's it. And that's intentional, right? Is that when you compare it to all the alternatives, it is so much simpler, right? So like compared to REDIS, where there's no automatic failover, right? Where etcd is just a multi-master system, more or less. A single master but automated failover for you, basically, where you don't have to think about that. It's built in by design. You don't have to roll a watch system. There's no watch system in Redis, so I had to like build a clever one with PubSub, where I like got things wrong, compared with like MySQL or Postgres, right, where you have to like run this kind of like untested alpha software. You still have to come up with a failure HA scenario, right, for something to do promotions when your databases fail. It also means that you have to stand up an entirely separate system for actually like keeping the event log, which means running like Kafka. It means running Zookeeper to run Kafka, or even other things that I looked at were like DynamoDB, where you have like a streams implementation that's extraordinarily difficult to work with. Because in addition to having like multiple partitions of streams, they will just fork on you so that your like number of partitions like keeps multiplying. You have to keep track of when they've split. It's very difficult to work with to get to a point where you can say something as simple as, okay, I got all of the data, now where do I start reading from the event stream, when you have like 10 different partitions and they keep splitting on you. Additionally, there were other things about it that made it difficult to work with, like there were no cross-object atomic operations, which etcd provides as well. So the next question is kind of like, when do I move the tunnel map to etcd, because that's still using Redis? And the answer is probably never. There are additional complications in the tunnel map that make it very difficult to build on top of etcd. Although I do actually have like a prototype that uses it in a more complicated way that I can tell you about afterwards. But basically, managing all of the custom indices in Redis is a pain, but doing it in etcd is even harder. One, because you don't have the rich data structures that Redis provides you, like sets and hash maps and sorted sets. And it's even more difficult from a performance standpoint because there are a lot of operations when you're basically manipulating those indices, where you pull out an object and you inspect it, and then based on what's in that object, you inspect another object. So basically, range gets won't help you in this sort of scenario, where you actually have to make a number of network round trips to gather all of the state you need to decide whether an operation is valid or not, and then once it's valid, what to do about it and what keys to update. So this is why I've been like lobbying the etcd team that they need to add like some sort of scripting, some sort of like way to inject custom operations into etcd, because I think it would be really powerful, and they have rightly and respectably said, no, that's not what we're trying to build here. But I think it would be really cool. I've actually even thought about like forking the code to actually do this, because I think it's such a powerful primitive to have, being able to basically build your own custom application logic into this like really nice replicated, consistent HA system. So takeaways, event sourcing, it's nothing new. It's just replicated state machines, but it is like a really helpful design pattern for certain sets of use cases. And the number of different ways that you can implement it is kind of mind-boggling. And so deciding on exactly the right set of technologies that you want to put together to build this sort of system for yourself is often a very difficult decision that requires really scoping your problem to decide what it is that you value, right? So in like building this, like one of my like things was like, what is like the smallest amount of work that I can get to do this? Like what technology like basically has all of these things that I can leverage immediately to get there. And the answer is like etcd is a really, really fantastic tool to build on top of, to build that sort of system. And that if all you need to do is keep a small, if your application state is basically a small working set and can fit into memory on any single box, then this is actually like a very reasonable way to build an event sourcing system. And that's all I've got. Thank you very much. So I think we have a couple minutes for questions. So if anyone has questions, just, hold on, we got a microphone coming to you. And for any questions I don't get through, just come find me afterwards. Happy to talk about this.
Hey, so you had a REDIS on every edge node with some crazy Lua script.
Sorry, can you speak up?
Sorry, you've got a REDIS on every edge node with a crazy Lua script inside it?
No, there's like a Redis, sorry, do I need to repeat the question? The question was, is there a Redis instance with a crazy Lua script on every edge node? And the answer is no, there's a Redis instance in every data center, more or less, along with a replica for failover, and all the edge nodes are subscribing to that particular Redis master, more or less.
So would it, if the data fits in memory, why not just write your own service which stores it in memory in whatever language you want and so on?
That's a great question, and the answer is basically because the same reason I'm like leveraging etcd is that it gives me nice things like replication and easier failover and snapshotting and things like that.
Cool.
What sort of performance are you sustaining with this? I mean, is it hundreds of operations, tens, thousands?
Yeah.
Any thoughts on the difference between the performance of Redis and the performance of etcd?
Sure. So the question is about performance, how etcd compares to Redis, how many operations does this do? And the answer is that the etcd, the data that's in etcd changes extraordinarily slowly, and performance basically does not matter for that. In terms of throughput, the performance doesn't matter so much. What does matter is latency, and the latency of etcd operations on the order of milliseconds is totally fine and not a worry. The time is really dominated by the actual like synchronization from across the globe, from the network connection from local data center to global data center. So it's really not a problem combined with the no throughput problem. So I haven't actually measured that because it's just not been within the scope of the problem. Cool. Thank you all for coming. Come find me afterwards. Thanks.